All right. Yeah. Hello, everyone. Good afternoon, and let's get started our lecture number 10 or 11. I guess I confused the uh, numbering in the on the YouTube. So on YouTube it's gonna be 11, and the previous one, I mean, according to my uh, lecture notes, it was 9 last week. So yeah. So anyways, lecture number no, lecture number 10. So the let's quickly recap what we've done last week, right? So last week we have started our discussion on the quantum algorithms, and last week we discussed the first, well, the first circuit or the first algorithm. We call this golden single qubit circuit, and it relates to the concept of quantum interferometer. So the quantum interferometer consists of two Hadamard gates, opening and closing Hadamard gates, and the phase qubit P F that is sandwiched between two Hadamard gates. Okay, and the purpose of the first Hadamard gate is to open the interference. Then the phase qubit changes the phase in a controlled way, and the last Hadamard gate closes the interference, so we can see the result of the effect of the phase qubit. All right, and then of course we measure the circuit in the end by putting the measurement gate, and according to our result, the result of the measurement, the probability of detecting 0 or 1 at the end of the circuit depends on the phase of the phase qubit in a controlled way. So for example, there are some phases, values of the phase when we can detect only 0 and a 0 state, and can't detect 1 or state 1, for example, for the phase 0, or for the phase what it is, 3 pi over 2, right? Yeah, it's gonna be state 0, and the state 1 we can't detect it in the measurement. So yeah, so this type of the interferometer is known as the Ramsey interferometer. And in general, this type of the device is a nice example of a quantum algorithm or quantum approach when we have a multiple opening Hadamard gates and closing Hadamard gates, and some circuit or some algorithm sandwich between these two layers of Hadamards. Okay, and the purpose of this circuit between the Hadamars is to operate with the phases of the quantum state in a controlled way. So in the output of the circuit, we've got the answer. So we have some input in the circuit, and our answer is the amplified amplitude for the particular state. So if we encode our problem in the input or in the state of this function f, as we will discuss today, the answer will be the amplified amplitude of the state that corresponds to the one particular quantum state. All right. As a second example, we've discussed the algorithm for the quantum teleportation of one qubit state to the exactly the same state, but on the other qubit. Okay, so it's not transfer of matter or transfer of information. This is the transfer of the quantum state from one qubit to another qubit. And this is important because in quantum we have this no cloning theorem, which imposes which implies the fact that we cannot clone a quantum state in a way we clone or save, reproduce the state of a classical system. So in classical system, we measure the state of a qubit or of a bit, right, of some system. We measure it, and then we can save or prepare another system in exactly the same state. So in quantum is not possible, and the only way is to teleport the quantum state from one qubit to another qubit, even though we don't know the exact quantum state, we still can teleport it from qubit to qubit. So here is the procedure. Here is the algorithm for doing so. And today we continue our discussion on the quantum algorithms. And today we're going to discuss this important case of a quantum algorithm is known as Grover's search algorithm. So the title of today's lecture is Grover's search algorithm. Okay. So the Grover search algorithm is very much based on this idea of opening and closing Hadamard gates, and the first layer of the Hadamard gates is used to create the uniform superposition of the computational basis states. Okay, so let us briefly remind ourselves what it means. So for the single Hadamard gate and for the input state 0, we know that we get the output state plus, right, which is 1 over square root of 2, 0 state plus state 1. Superposition of two computational states, state 0 and state 1. For the system of 2 qubits, initially also in the state 0, we would get the of course in the input we can write it as a tensor product of 0 times 0, right, which is state 0 0, and in the output we also get the tensor product of the result of the first qubit, which is 1 over square root of 2 0 plus 1, and is exactly the same for the second one, but I write the tensor product 0 plus 1. Okay, which gives us the state 1/2, then states 0 0 plus state 0 1, plus state 1, 0, then plus state 1, 1. So 4 possible states, which is exactly 2 to the power of n, right? Where n is the number of qubits. So if in general case of n qubits, number of qubits, the general state of a system of n qubits will be presented by the string of n capital elements with the number of 2 to the power of n number of elements, right? For example, for a system with 3 qubits, this superposition will contain 2 to the power of 3, 8 terms, 8 elements, and etc. But let us look at this expression one more time and enumerate these computational basis vectors like 0 state, the first state, second state, and the third state. Okay, this will be useful like to represent a state in a general system. So for the 2 qubit system like this with 2 Hadamard gates, I denote the uniform superposition state as the vector S, okay? And I can write this expression in the following way. So it's gonna be 1 over, so 1/2 or 1 over square root of 4, okay? And then the summation over the states, computational states x. So this x stands for 0, 0, 0, 1, 1, 0, 1, 1, or states 1, 0, 1, 2, and 3. So in terms of states 0, 0, 0, 1, 1, 0, 1, 1, I can rewrite this summation over x that is the all possible combinations of 0 and 1 with the length 2. Okay, so all the possible combinations of the of zeros and ones with the length 2 digits, which includes obviously 0, 0, 0, 1, 1, 0, and 1, 1. Okay, so this is the way how we basically write the same state, the same expression in terms of in the more condensed notation. Okay, and in terms of states 0, 1, 2, and 3, I can write the same in the following way. So again, the normalization factor 2 to the power of 2, okay, and then summation over again x from 0. So in this case, my x state is numbered from 0 to 3. So, and 3 is 2 to the power of 2 minus 1, or 4 minus 1 states, and I enumerate them by vector x. So in this form, this x is state 0, state 1, state 0, state 1, state 2, state 3. Okay, so this is the way how we can represent the states for example, this superposition, uniform superposition state in a condensed form that will be useful for what follows. So in the this is the superposition state for the system with 2 qubits. And now I can generalize this to the system with n qubits, and instead of writing like n lines for the system with n qubits, we can simply combine all of them in one single element like this. I still have 0 in the input, and then I draw the line like this and put n. So this n represents the group of n qubits. And then if I need to apply the Hadamard gate to each of these qubits in the group of n, I write it like this, or I denote it like this. So I put this Hadamard sign and then tensor n. Okay, so it's applied n times, or which is the Hadamard gate applied to each of the qubits in this group of qubits. So I have the n qubits in this system, and in the input I have this state 0. And now what is the state in the output here? Right, input is 0, and I write this 0 in the each qubit. I combine all of them using the tensor product, and I write this like a state 0 to the power of n. Okay, and what is the state here in the output? How we can write this state using this dense notation? So using this dense notation, I can write the state S, which is the perfect uniform superposition of the all states. Again, it is the result of the application of the Hadamard gate on every single qubit in the circuit. And initially each qubit is in the state 0. Okay, and the result of it will be the 1 over square root of n capital, which is the number of possible states in the system, right? N capital is 2 to the power of n small, and n small is the number of qubits in the system. Okay, so 1 over square root of n, and then summation that runs over the number of the state, runs from 0 up to n capital minus 1. If I number the states from 0, then the last one will be n minus 1. Okay, and state x, which encodes the number of the computation state basis. And the same can be written. So this is the this part is a generalization of this part for the 2-qubit system to the system with n qubits. And now I can write this part also, which gonna be 1 over square root of 2 to the power of n, right? and the summation for x, that is the all possible combinations of zeros and ones with the lengths n small. All right, and x, of course. All right, so this is the way how we represent the state of the uniform superposition of all computation basis states. Let us maybe denote this uniform superposition of all computational basis states. This vector S. All right, and so now let's talk about the Grover search algorithm. And in order to gain some intuition in this search algorithm, in this quantum algorithm, let us consider the following picture. So I'm gonna represent the entire Hilbert space on a plane or in a two dimension. Okay. So this Grover search algorithm, the purpose of this algorithm is to speed up the search among a large number of elements. Okay, so these elements can be literally anything. It can be words, it can be numbers, it can be telephone numbers, maybe pictures, etc., and so on and so forth. And the way it works is we first have to encode these elements in the states of in the computational states of the quantum computer. Okay, and then the Grover's algorithm applied in a way that it maximizes or amplifies the state of that corresponds to the element of our interest, of the element of we after. Okay. So in other words, we encode some information into the state vector, and then we search for this state vector. So let us write this state vector like this and denote this state vector by state omega. State omega first. And in order to form the like a Hilbert space based on this, I mean, from this vector, we need another one, another orthogonal vector, orthogonal to this vector. Which is our we can computer right? Our algorithm starts from creation of the uniform superposition of states S. So basically this state S here, okay? So the oops, I have some troubles over here. Okay, so we can write the vector state of this uniform superposition in this space like this. So this is the vector S. Okay, and let's denote the angle between the vector S, which is known, right? This is the vector of superposition of all states. So it's the same for any system. And let's denote this vector by theta over 2. Okay. Let's also maybe write down this information here. So this state omega is the state we search for. So we search for this state. Okay. And the omega horizontal, omega orthogonal, is the orthogonal state to the one we after. The orthogonal state. Orthogonal state to the one we after. What it means that the inner product of the vector omega and omega orthogonal is supposed to be equal to 0. Okay, so the vector omega contains no vectors, no components parallel to the vector omega orthogonal. So how the Groover's search algorithm works, like in general, in this schematic representation. So we first reflect this vector state S, which is the uniform superposition of all computational basis vectors across the orthogonal vector omega orthogonal. Okay, so we reflect across this the vector S across the vector omega orthogonal like this. It means that we rotate this vector S over the vector omega orthogonal by exactly the same angle theta over 2. Okay, so this way we've got a new vector, and of course this rotation is realized by application of some unitary operator or unitary matrix, and we denote this matrix by U omega orthogonal. Okay, so it's a matrix that rotates the state vector S across the or over the vector omega orthogonal. Okay, so this is our new vector. So this is first, and second operation in this algorithm is a reflection of this new vector U omega orthogonal over the vector S. So we reflect now this vector U orthogonal over the or across the state vector S. Okay, so it's gonna be the same angle, theta over 2 plus theta over 2, which is exactly theta. And the new vector will point into this direction, obviously. So it's gonna be this new vector, and the angle between this new vector and vector S gonna be theta. Okay, so we did two reflections, and as a result of these two reflections, we've got the new vector u, which is denoted by this index S. So it's a reflection across the direction of the vector S, and it acts on the state u omega orthogonal S. Okay, so it's a state of new vector, and we notice that after these two reflections, first across the vector omega orthogonal, okay, and then across the vector S, which is the uniform superposition of all possible states or computational basis states, we've got new vector, this magenta color vector, which is now lies like closer to the state that we are searching for, to the state we're after, this omega state. Okay, an idea behind this Groover's Groover search algorithm is that we can apply these double reflections multiple times, and each time we apply this reflection, the resulting vector will get closer and closer and closer to the state we are searching for. Okay, so for example, now the next iteration would be rotation of this magneto vector over, or reflection this magneto vector over the state omega orthogonal. Okay, so it's going to be some vector pointing in this direction. Okay, and then rotating this or reflecting this vector again over the state S, this blue state, which will return our state somewhere here. Okay, so it's gonna be a new vector which will be even closer to the state we are searching for. And of course, the closer this new state to the searching for, to the one we search for, means that after the measurement, as a result of the measurement, with a higher probability, we will get the result, or this we will get this omega state, or we got this omega. So this is how the Groover search algorithm works in like schematically. And now let us talk about a circuitry of this algorithm. So as we discussed, we always start from the zero state. Okay, so the zero state or the ground state, typically it is a state of unexcited qubit, which is naturally in the zero state, or it can be prepared in this zero state. Anyway, so we start from the zero state, and then we have a system of n qubits. Okay, so I'll draw this line slash and n. So this n means that we have the parallel n lines in this circuit. So it's this circuit, this quantum register consists of n qubits. Okay, so we first create the perfect superposition state of all these n qubits by applying the Hadamard tensor n, okay, which means we apply the Hadamard to every qubit in this register. And in the output, of course, we've got the state S, which is denoted here. Okay, so this is the state S in the general case of n qubits. So then, according to our discussion here, so first we reflect the state S across the vector omega orthogonal by applying the circuit, or well, the combination of gates. We denoted by U omega orthogonal. Okay, so this gate rotates the state S across the orthogonal vector omega orthogonal. And then we apply the another part of the circuit and of the circuitry, which rotates the resulting state across the state across the vector S, the initial vector S. Okay, it's denoted by US. So as a result of this operation, of this single operation, we've got the vector US U omega orthogonal S. Right. So this is the result of single iteration. And then in a general case, we need to apply this part of the circuit multiple times. Okay, and it's called Grover iteration. So we need the Grover iteration in the general case. So let's denote it by this rectangular parenthesis, like to the power of R. So I apply this part of the circuit multiple times in order to get my resulting state to the state I'm searching for. Okay, so this is Grover's iteration. Grover's iteration. And then finally, I apply the measurement gate, or I measure the qubits in their state, and this measurement returns the classical number, right? 0 or 1 with some certain probability, and this is the outcome or outcome of the circuit, or of this Grover's algorithm. Like few words about the naming of these operators, U, omega, and US. So the operator or operation U omega orthogonal, or U omega, it's called oracle. And so this oracle is a function that returns So it works like a black box. You ask so you design the oracle in order to return the answer either either 0 or 1, depending on the depending on the uh, what you are looking for, what is your element you are searching for. Okay, so we will discuss this in a while today. So, but I mean, in general, the oracle is just a function that you design to do some operations. Okay, and another one, this US, is known as amplifier. Amplifier, and the purpose of this operation is to amplify the amplitude of a state that you are searching for. Okay, so so you apply these two operations like together, oracle and amplifier. Oracle is designed for each for the different calls, for the different search. One designed this oracle. Amplifiers is pretty much the same for any search. We've got the question in the chat. By amplitude, do you mean in the state vector or probability? The amplitude, of course, of the state vector. So you have the in this case, what we amplify is actually the probability, of course. So we amplify the probability of finding or detecting the state we are searching for in the classical measurement. But of course, this also means that we amplify the amplitude of the state vector. Because this is not like, so this amplification is in terms of constructive or destructive superposition. When you have the constructive interference, the resulting, for example, if you have two waves, they constructively interfere, the resulting amplitude is 4 times larger, right? Because you sum up the two amplitudes and then you square the result for the actual probability. So the probability is enhanced by a factor of 4. Yeah, so as I said, the amplifier is pretty much the same for any search, for any algorithm, but the oracle is to be designed for specifically for searching some particular elements. And one particular oracle we will discuss today when we will describe an example of a 2-qubit circuit, which is trivial but still nice in terms of it's a nice example. All right, so oracle and amplifier. Few words about this state omega. So the state omega is the state we are searching for, okay? And this state omega is one of the states X. So I remind you that this state X, it enumerates all possible computational basis state vectors in the of our computer, of our of the Hilbert space of our computer. For example, if our computer gets only 3 qubits, then we have 2 to the power of 3, 8 possible basis vectors, 8 vectors, and this x denotes all of these 8 vectors, and the summation will run from 0 up to 7. So this state omega is just one of these basis vectors. Okay, like if I need to do search among 8 elements, so I have a group of some elements of 8. Okay, it's a small number of elements, but representative. And I need to search for one particular element in this group. I denote the particular element in this group of 8 by this omega. Okay, and this vector omega represents the vector of this element. Okay, and I designed this circuitry, I designed this algorithm in order to for this computer, for this algorithm, starting from the 0 state in all 3 qubits, the result of the measurement gives me the element I am searching for. Okay, so this omega state is one of the states x, is one of x. Okay. So at the same time, we know that the state vector S, which is the vector of superposition of all these states x, right? So x is the superposition of all states x. Okay, so it means that if we subtract the state omega, if we subtract this state omega from the state S, we will get exactly the state omega orthogonal. So omega orthogonal is given by the subtraction of the state omega from the state S. So state S minus state omega. Why? Because when I take a product of this state omega orthogonal by the state omega, okay, all states in the S being applied, being multiplied by the state omega will give me 0, except for just one, which is parallel to the state omega. Okay, and if I remove the state omega from the state S, then there will be no state which is collinear, which is parallel to the state omega, and the result will be 0. So because the inner product of omega and omega orthogonal is 0, or supposed to be 0. Okay, so let me repeat this once again. So the state S is the superposition of all basis states. Okay, the state omega is one particular basis state, which encodes some information that we search for. Okay, so next, if I remove this state, particular state omega from the all states S, there will be no states anymore that is parallel to the state omega. Okay, so this new state S minus omega will be definitely orthogonal state to the state omega. Okay, all right. So in this case, we can write this new orthogonal state as follows. So it's gonna be omega orthogonal. The normalization factor will be different because we have one element less in this span of the vectors, right? So it's going to be 1 over square root of n minus 1 in this case. And again, summation of all possible states x in this of this computational basis, except for, so we exclude the state omega. Okay, we exclude the state omega. So this is the way we represent the orthogonal state. And of course, if I take the inner product of omega state and omega orthogonal, I will get 0 because the omega orthogonal state doesn't contain this omega state anymore. Very good. So at the same time, let me return back to this picture. At the same time, we use this omega state and omega orthogonal state as the basis to represent the other vectors in this Hilbert space. And we of course can represent this state vector S by the projections of these vectors to the basis vectors omega orthogonal. Right? So how we do so? So we can write this vector S in the basis omega orthogonal by projections of this vector S on the corresponding vectors. So it's going to be omega projection S vector, right? So it's a projection of the state vector of the vector S on the basis vector omega orthogonal times the vector omega orthogonal, and the same for the vector omega. So it's going to be a projection of S on the vector omega times vector omega. Okay, so it's just a representation of the vector through its projections on the orthogonal vectors omega and omega orthogonal. At the same time, the projection of vector S on the omega orthogonal, this line here, right? This is the cosine theta over 2. So this part is equal to cosine theta over 2. And this guy is sine theta over 2, obviously. Okay, so we can represent this like cosine theta over 2 state omega orthogonal plus sine theta over 2 state omega. Okay. On the other hand, we can calculate this sine and cosine by writing the projections in a explicit form. So, for example, for the state omega inner product with state S, we have omega, right? And then for the state S, we have this 1 over square root of n capital and summation over all possible states from 0 up to n minus 1 state x. Okay. Okay. So state omega is one particular state in the basis denoted by x. So x here denotes all possible states. State omega is just one particular state. And all these states are orthogonal, which means the product of this omega with all x give us 0, except for just one, which coincide with the state omega. And this product gives us 1. And the result will be just 1 over square root of n. Okay? 1 over square root of n. Okay, similarly, for the state omega orthogonal, which is now a combination of all states except for the state omega. Okay, so this the same way omega orthogonal, we multiply it by this vectors s, which is 1 over square root of n, x runs from 0 to 1 n minus 1, state x. And here we can show that the result will be square root of 1 minus 1 over n. Okay. So why? Because the product, for example, of s by s. So when we take the product of all this, the superposition of all vectors by the same gives us 1, right? But this vector omega orthogonal is all this superposition minus the one particular vector omega, okay, which gives us 1 minus 1 over n. And then for the normalization vector, we get this square root. Okay. Or similarly, if I take the square of the first of this one, right, and plus square of this one, I would get exactly 1 because of the normalization. So anyways, we just get the result that that sine theta over 2 in the angular representation is equal to 1 over square root of n. Okay, so I just compare this one and this one. They must be the same. And likewise, this guy and this guy also must be equal. So cosine theta over 2 must be equal to 1 over square root of 1 minus 1 over 1 over n. All right. So this is about the vectors and how these vectors and their projections depend on the number of qubits and the dimensionality of the Hilbert space. So now we need to discuss these operators US and U omega. So let's start from the operator US. So let's now we write operator of reflection across or over state S, right, which is the US operator. And the result is the following. So this operator US is equal to 2 times the projector SS minus the identity operator. Okay, so let us, this is known fact, let us show that this is the case. So in order to show that this is the right operator of reflection of any vector over this vector S, we can consider two examples. So first, the application of vector S, application of this vector on the vector S. So when we have, for example, the vector S, this is the vector S, and I reflect any vector across this vector S. And of course, if I apply this operator to the vector S itself, I will get exactly the same vector S, right? So let us check that. So when I apply this US to the vector S, I would get what? I would get 2, then vector S, then S, then apply this S, minus identity. So this I is an identity operator, S, which is equal to. So this S times S, because the vectors are normalized, right? It's 1. So and the result is 2 vector S minus identity operator applied on the vector S gives me vector S. So it's the result is the vector S. So nothing is changed. This is the first. Second, I consider the orthogonal vector to the vector S, this one. Okay, this one. This is the S orthogonal. And I apply this operator of reflection over S to the orthogonal vector S. What would I get in this result if this operator is correct? I will get minus vector S orthogonal because the reflection of this one gives me the new vector in this direction, right? So it's going to be minus vector S orthogonal. Let us check that. So US applied to the orthogonal vector S is equal to 2 vector S, then vector S orthogonal. Okay, then minus identity vector S orthogonal. Again, because this vector S is normalized, so since this vector S orthogonal is orthogonal to the vector S itself, right? This result will be equal to 0. So no projection of vector S orthogonal to the vector S. And the result will be equal to identity operator times vector S orthogonal is vector S orthogonal. So the result is minus vector S orthogonal. So indeed, this operator here represents the reflection of a vector over the vector S. Okay, and in general case, for any vector state X, if I reflect it over the vector S, it's gonna be 2S cross S vector X minus identity vector X. So this is in the general case. So this is reflection of state of the vector X over vector S. Another point, important fact here is that we can represent this operator as a sandwich between the two Hadamard operators. Okay, so let me write this like this. So this operator of reflection of any vector over the vector S can be written as, so let me rewrite this again. So this operator can be rewritten as the Hadamard tensor N. Okay, so the Hadamard applied to all the qubits in the circuit. Then goes this this line 2, then 0, 0, and this 0 states to the power of n, which denotes the vector of all zeros, right, in the string. And again, n is the number of qubits. Minus identity times the Hadamard. Okay, so this is exactly the same representation, and one can check that. So it's pretty straightforward. So vector S is the result of application of the Hadamard on the zero states. Okay, so if you apply this Hadamard from here, you will get this part, and this one applied here, you'll get the same. And Hadamard applied on the identity from both sides, it's equal to the application of the Hadamard, times Hadamard, which is 1 because this operator is unitary. So you will get the identity matrix I. So it's exactly the same. But at the same time, in terms of gates, it will allow us to represent this operation in terms of quantum gates, right? First, it will be the Hadamard gate, then some another circuit part, and then Hadamard gate again, and it represents nicely this statement of quantum computation when we open the quantum interference with the first Hadamard gate, then we do something with the phase, and then we close the Hadamard gate in this circuit, as we discussed last week. All right, so this is about the amplifier, right? This is the operator of amplifier. So now we need to define the operator of the oracle. So oracle. So this concept of oracle is not unique for the Grover's algorithm and the other quantum algorithms. For example, this Deutsch algorithm. They also all based on the concept of oracle. So oracle is a function that you ask something and it returns something uh, in response. Okay, and in terms of matrices, this oracle can be written in the following way. So let us say that the oracle, the operator of the oracle for our operation omega orthogonal gonna be the diagonal matrix was denoted by D. Okay, so it's diagonal matrix. Diagonal matrix with all 0 elements, but the elements standing on the main diagonal, and these elements will be minus 1s to the power of f of 0, then minus 1 f of 1, then minus 1 f of 2, and all the way up to minus 1 to the power of n f of n minus 1. Okay, so this is just matrix with these coefficients. We can denote this oracle operation in terms of functions f. So this function f, right? This function f, it gets the number as an input. Okay, so it can be 0, 1, etc., all the way up to n minus 1. So this is the input of the function. Of the oracle. Input of the oracle. And for all these, for each input from this amount of possible inputs, right? For each input, this oracle function, it returns either 0 or 1, depending on the on the desired the search result, let's say this way. So the oracle maps the input to either 0 or 1. Maps input to zeros and ones. Okay, and then so oracle returns either 0 or 1, and then if the result, if it returns 0, then we've got these elements here in this matrix minus 1 to be to the power of 0, which is 1. Okay, then, and the same way for all the elements except for the elements with when this function returns 1, which gives us minus 1 to the power of 1, which is minus 1. Okay, so basically this operator, this oracle operator, it flips some of the phases of some of the qubits in a certain way, like for example, well, we will discuss the example of two qubits today, and that example will be like based on flipping one sign, this putting one minus before one of the amplitudes in the superposition. Okay, so the purpose of this oracle will be to flip the sign in one of the terms, one of the amplitudes, and this changing of the sign will enable the this search procedure. All right. Yeah, so this is in general how the Grover's algorithm works. Okay. Let me repeat, or actually let's write this down like the following. So the algorithm. So suppose you have a database, like some maybe classic database. So we translate this database to the orthogonal quantum states, to the basis states. Translate to basis, to the quantum basis or computational states. Okay. And we do search among these elements for the one single state in this array of the states, which is denoted by, in our case, is denoted by omega state. So we search, the goal is to search for this particular state among all possible states in the superposition. Okay. In order to search for this state, we need to generate or prepare the quantum oracle. Which is basically the form of this operator U omega orthogonal. Okay. And then we repeat the operation U omega orthogonal US multiple times to get the state, as close as possible to get state close to the state omega that we are after. Okay, so as close as possible to this state. So now here's the question: how many times we need to how many times we need to repeat this operation of oracle and an amplifier in order to get to the correct result. Okay, so let us estimate this. So above we found out that the projection of the let's know this one. How many times to repeat this Grover's iteration. Okay, so we know that the projection of vector omega on the vector s, or vector s on the vector omega, is equal to 1 over square root of n on the first from the one side, and on the other side, on the other hand, it's equal to sine theta over 2. Okay. So typically, or preferably, this number n is a very large number. Okay, because if this number n is small, then the number of elements in the search is also small, so it's trivial problem, and all this makes sense only if this n capital is a large or very large number. So we assume that this n capital, which is the number of basis states in the Hilbert space, okay, or 2 to the power of number of qubits in our circuit. So this number is very large. It means that the since n is very large, then 1 over square root of n is very small, right? So it means that sine theta over 2 is also to be small. And if we tailor this sign, we will need to take very first term in this series, which is theta over 2. Okay, if n is very large. If n is very large. Okay, so let us find the probability of measuring omega after a number of iterations. Okay, so the probability of measuring omega after r iterations. So for the 0 iterations, we would get something like this. So the probability of measuring omega after 0 iterations is gonna be just the square amplitude or square modulus square of the projection omega s, right? So this is the probability of measuring omega after 0 iterations. And in our case, this projection is equal to 1 over square root of n. So the result gonna be 1 over n. Okay, or sine square over theta over 2. So this result 1 over n for the probability of measuring omega implies that, or indicates that this probability is very small because n capital is very large number. Okay, so when we have a large amount of elements in our database, then the probability of getting the correct result by I mean, after one choice, one search is equal, very small. This very small number, as we supposed to. I mean, as it's supposed to be. So next, the probability of finding omega after r iterations is gonna be equal to, again, the absolute value squared of omega, and then instead of s, we're gonna get the a new vector, right, which is the operators u s omega. Oops, it's supposed to be, is it, let me see, for the order, yeah, us u omega us u omega orthogonal r times multiplied by s vector squared. Okay, so this is still projection, but the projection of new vector new vector after application of this operator, of this Groover iteration operator by r times on the vector s. Okay, so each time we apply this iteration operator, we rotate or we reflect this state vector s, the superposition vector s, closer and closer to the vector omega. That's why, of course, the projection of this vector s on the vector omega increases. However, if we continue this procedure, we will pass through, or we will miss the vector omega, and at some point this projection will reduce, and we need to know the number of iterations that will give us the correct result. Okay, so this can be rewritten as the following in terms of the sine. It's gonna be sine, again, squared, but the angle gonna be theta times 1/2 plus r. So this simply comes from this description of the reflection of the vector s over first vector omega orthogonal, and then across the vector s itself. Okay, so each time we getting closer and closer to the vector omega. Okay, so yeah, so how many times we need to, or how many iterations, how many r we need? So of course this iteration must result in a probability that is equal or very close to 1, right? So the correct result will be when the probability will be like equal or almost equal to 1, which means that the sine squared of this theta 1/2 plus r is equal or almost equal to 1, and that means that this angle theta 1/2 plus r must be equal to pi/2. Okay, and after some simple algebra, we find that this r small is to be equal to equal to pi over 2 theta minus 1/2. So next, we already found that where it was, yeah, here. So the theta over 2 is equal to 1 over square root of m capital, right? So 1 over theta over 2 is equal to, or approximately equal to, 1 over square root of m. And from here we conclude that theta is approximately equal to 2 over square root of m. Okay, and now I can plug in this one to the previous result and get the formula for the number of iterations. It's going to be pi over 2, right? Then square root of n over 2 and minus 1/2. So n and square root of n is a very large number and definitely larger than 1 and 1/2. So since square root of n is much larger than 1, then we can omit this second term, this 1/2, and the final result is for the number of iterations is pi over 4 times square root of n. Okay, so this is the formula that allows us to calculate the number of iterations of the Groover's algorithm to get the right result. And we see that it scales as the square root of n. Scales as square root of n. So how it compares to the classical search algorithms? So let's suppose we have the array of elements, okay, and we've got, for example, n elements, and we are looking for a particular element in this array. Okay, let's suppose that, I mean, of course, the easiest way to search for the element of need is the just checking all these elements one by one. And of course, if the first, I mean, if the element of the need is the very first one, then we can find this element like quickly from the first try. But this element can be very last in the array, and then in order to get this one, we will need to make n-1 calls, right? Because if the previous one is not the right one, and we checked all the elements in this array, then obviously the very last one is the right result. But of course, if the number of elements is very large, this is n-1 will differ very, very small from the n, and the number of calls will be equal to, or approximately equal to n. And so taking all this into account, we can say that in average, the classical search requires n over 2 calls, or n over 2 runs to find the element. So the classical search requires n over 2 runs to find the element. Let us write this. Requires n over 2 runs. So it scales, it definitely scales as a factor of n. right? So the larger n, the larger number of runs to find the right element. In contrast, this quantum Grover's algorithm, it gives us the factor of square root of n. Quantum gives us square root of n, which is the quadratic speed up. Quadratic speed up. So for example, for a number of elements of 100, which is very small, right? So if number of elements 100, then classic would require about 50 runs. Classic would require 50, but quantum requires 10, which is not that significant improvement, and definitely doesn't I mean, it's not very practical to use the quantum computer or whatever to search among 100 elements. But when a number of elements is, for example, 10,000, which is still not that very important case, but already shows the point that, for example, in classical, we would need 5,000 runs of the search algorithm, but in quantum, we would need just 100 rounds, which is already significant improvement. So we're running out of time. Let us quickly discuss the I would say useless and trivial, but at the same time example that we can quickly run using quantum machine and quickly check using the quantum circuits. This is the case of two qubit circuit. Okay, so the section 4.3, let's say 1, 2 qubit example of Grover. 2 qubit example of Grover. So, so in this case, again, we encode the information in the state omega, and we can find the orthogonal state omega orthogonal, okay? And of course, we can prepare the superposition state as state superposition. And let's find this theta, right? The theta over 2 from the fact that so where it was sine, so it was sine from this factor over here. Okay, so sine theta over 2 is equal to 1 over square root of n. So sine theta over 2, which is this angle, theta over 2, is equal to 1 over square root of n. This result holds for any n, so no need for very large n. So it holds for our 2 qubits example. So in this case, over 2 qubits, it's gonna be 1 over square root of 4, which is 1/2. And it means that this angle, theta over 2, is equal to what? Pi over 6, right? Because sine pi over 6 is equal to 1/2. So this is pi over 6 angle. I apologize for the noise. All right. So next, for the 2-qubit system, we have n small is equal to the capital N is equal to 2 to the power of 2 is 4, as we already know. So the dimensionality of this Hilbert space is 2 or is 4. The superposition state in this case is equal to, as we discussed today, right? We've derived this today. Again, it was this state over here. So 1/2, and then the combination of all the computational basis vectors 0, 0 plus 0, 1 plus 1, 0 plus 1, 1. Okay, or using our condensed notation version, we can write 1 over 2, and then the summation of all x, where x is the all combinations of zeros and ones with the length 2. Okay, so this is the vector s, and what is the orthogonal vector omega orthogonal? As we know, we need to subtract the vector omega from the vector s, and at this point, let's say that we are looking for, or we're searching for the state omega, which is, for example, state 1, 1. So it's a classical example of searching for the state 1, 1. Okay, so the omega state 1, 1, and that means that the state omega orthogonal, which is, I remind you, with vector s minus vector omega, with the right normalization vector or normalization factor. So it's going to be 1 over square root of 3 for the normalization, and then 0, 0 plus 0, 1 plus 1, 0. No 1, 1 because we subtract this state 1, 1 from this superposition. And indeed, if I take the product of inner product of omega and omega orthogonal, I will get 0. So these two vectors are orthogonal. These two vectors are orthogonal. So how many runs we need to apply the Grover's algorithm? Let's define this. So for the number of iterations, we have this approximate formula pi over 4 square root of n, right? Which gives me pi over 2, which is about 1 iteration. About 1 iterations. So we need just 1 iteration to get the result in the case of 2-qubit circuit. Why so? Well, it's very easy to see from this graphical representation. So what I do, again, I need to take this state vector s, the superposition state, superposition vector s, and then reflect over the vector omega orthogonal. And this angle will be also pi over 6, okay? And then pi over 6 plus pi over 6, which is 2 pi over 6, which is pi over 3, right? I need to reflect this new angle, this new vector, over the state state S by a factor of pi over 3. And that will give me exactly this direction of the vector omega, because this is the angle pi over 3. Okay, so even from this graphical representation, we see that we need just one iteration of the Grover's algorithm to get the result. And finally, what is the oracle? So what is the oracle in this case? So the oracle in this case is a function which takes zeros and ones in the, or states 0, 0, 0, 1, 1, 0, 1, 1 in the input. So I denoted by zeros, ones of the length 2, right? And returns the digits 0 or 1, depending on if the result of the choice is or if this answer is correct or not. And for the wrong result, if the state is not the state we are searching for, the result is 0. So, and for example, for the state 0, 0, this is not our state, right? So the result, the return will be 0. The state 0, 1 is also 0. The state 1, 0 is also 0. But state 0, but state 1, 1 is the state we are searching for. So it must return 1 here. Okay. And according to this recipe of creating the of the operators here, okay, I need to take a power. So this the operator of corresponding oracle will be a matrix, diagonal matrix, with the elements -1 to power 0 is equal to 1. So these 3 elements must be equal to 1, but the last one must be equal to -1, because -1 to the power 1 is -1. Okay. So this is the oracle for 2-qubit problem, for 2-qubit problem. Oracle for the 2-qubit problem. If I present this matrix 1, 1, 1, -1 in its actual form, it's gonna be 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, -1. Okay. So this is known as the matrix of the controlled Z gate. It's a control Z gate. We didn't discuss control Z gate in the part about the 2-qubit gates, for the fact that this control Z gate is it can be represented through the combination of Hadamard gate and control X gate. So CZ, the control Z gate, can be represented as Hadamard gate times control X gate, and finally times Hadamard gate again, and Hadamard gate applied to the target qubit. Okay. So no need to discuss specifically control Z, but the operation is the same or similar to the control X. Control Z, it acts as a Z operator depending on the state of the control qubit. If the state of the control qubit is 0, then it leaves the state of the target qubit unchanged. But if the control is 1, then it acts as the Z operator to the target qubit. Okay, so having all this in mind, we can write down the actual circuitry for the Grover's algorithm for the two qubit system. So again, we start from the state 0. Then we need to apply this Hadamard here and here to create the superposition state. Okay, so here by these two Hadamards, we create the superposition state. Then the oracle, as we discussed, the oracle is just the control Z gate, control Z gate. So this is the oracle. In this particular case, or omega, the operator U omega orthogonal. Okay. So after that, we need to apply the Hadamard here and here again. Then we need to apply the Z operator, Z gate, to the first and to the second one. Then we need to apply the control Z gate again. Then we apply the Hadamards again to close the interference. And then finally we measure the both qubits. Okay. And if we write the result of this measurement must return only one state, which is state 1,1. Okay, so this is the oracle. This guy is the oracle here, and the amplifier, right? The amplifier is this part of the circuit. This is amplifier. The state here is S. The state here is U omega S. And finally, state here is U S, U omega S. Okay. And we need to apply this oracle amplifier just once to get the right result. Okay, so this is the circuit. Now we can go to the Quirk, for example, and check that our circuit is correct. So do you see the screen with the Quirk? Anyone? Okay, in the chat, yes. Thanks, Andreas. All right, so what we do, we apply the Hadamard first to the first and the second to create the superposition state, right? Then I need to apply the control Z. So I apply control and then Z, and this Z automatically converts to the control Z here, right? So then, according to the procedure, I apply the Hadamars again, and then Z Z gates again. Then I need to apply this Control Z again, and close the interference by applying the finally these two Hadamars. Okay, so as we expected, the result is strictly perfectly state 1-1. Okay, for example, without these Hadamars, we have some combinations of these states, but when we apply these Hadamars, finally we get perfectly state 1-1. So let me so this of course is trivial circuit, and no one would need to use these quantum circuits for searching among just 4 elements, as in this case. But let me repeat how it works. So we're starting from the 0 states, then we create the superposition states S, which gets 4 components, 0, 0, 0, 1, 1, 0, 1, 1. Okay, and then we program the oracle, which in our case this is just the gate Control Z. So we program this oracle in order to be able to find the state 1-1. If it would be another state of interest, like state 0, 0, this oracle will be 0, or this oracle will be different gate or combination of gates. In this simplest case of the searching for state 1-1, it is just Control Z gate. Okay, then we design this amplification, the combination of Z and so the combination of Hadamars, then Z gates, then Control Z, and closing the Hadamar gates. So this amplification circuit is pretty much the same for any circuit, for any search, and it's designed in a way like in the way to amplify the probability of finding, of detecting the state of interest. Okay, and in this case, indeed, for the chosen oracle, we get state 1-1. The same can be, of course, designed in a IBM quantum. Right, so in this case we have to again start from application of 2 Hadamars. Then I need to apply the oracle, which is Control Z. So I have Z here, no Control Z, but I can modify this Z by adding the control to the A. Okay, it's perfect Control Z qubit, which is denoted by like a different comparing to the quirk. So what is next? 2 Hadamars, Hadamar here. We can see nicely how the states change when we apply the gates. So next is Z gate here and here. Then the Control Z again, so I can copy and paste the gate, and finally closing the so H, Z, Control Z, and finally closing Hadamars. Okay, and the resulting probability is exactly state 1-1. So after application of one Grover's algorithm, we got exactly the state 1-1. And then, of course, we can run the simulation, and in order to be able to run the simulation, we need to add the measurement qubits, or sorry, measurement gates. in order to measure it. And then some time ago we discussed, right, how to run the simulations. Of course, the easiest way to run quickly the simulation is to go here, click setup and run, and then choose one of the available quantum computers or simulators. For example, we can, for example, choose this custom simulator, right? Like the one we used for classical simulations of the quantum circuits, and run the simulation. And after it's run, the result appears in the jobs here. Okay, so this is the result of the simulation. Perfectly state 1-1. And before starting this lecture today, I sent this circuit for simulation to the real quantum computer, and it's still in the process. So it still says 2 hours. Yeah, so unfortunately this time, I mean, these days, the process of running of using quantum computers is very slow. It requires few hours in order to run even simple circuit. And so maybe next time we will check out the result of this simulation. It is in the line. And last week we've checked the result of simulation of the quantum computer for the Bell test, right? It was where it was. I mean, anyways, we discussed that already. Maybe this one. No, something else. Same. So 1 second, probably this one. Yeah, so this is the 2-qubit golden circuit, right, with the Hadamard gate here and the control X gate, and here is the result of the simulation. We discussed that last time. So I expect for this project something similar to this one in terms of getting like almost perfectly one state, like here for the classical simulation, and some contribution from other states, which are the simulation inaccuracy. All right, but we will check it out next time. So thank you very much for coming, and let me stop the sharing and recording, and we can discuss then.